So today's lesson is going to be about optimization problems, and today, instead of solving for the absolute minimum values of optimization, we're going to have a situation where we're solving for the absolute maximum values. So our scenario here is that we have a cone, and what's going to happen is that from bird's eye view, this cone, circle shaped, it's going to be like this. So you have a point, 1, 2, and 3. So when this line is connected over to this line, so you're connecting lines 1 and 3 to, 1 and 2 to 2 and 3, we want to know what the maximum capacity of the cup is. So essentially what's going to happen is that essentially just have the actual closed cone with some radius and some height. So in this case, we're going to have some height, some length r, and you're going to have some radius. And back to simple geometry, we want to find out what that r value is. Well, here you can see that we have a right angle triangle, and so it's as simple as just taking h squared plus the radius squared equals to big R squared. Okay, so that's finding R, and that's just a simple parameter that we're going to have to use. So, optimization problem, we want to find out the capacity of the cup. So in this case, we want to find out what the largest volume is going to be. And we know that the volume of a cone, and you can look this up on Wikipedia or something or anything, one of your textbooks or whatever, if you don't already know this, is pi over 3 r squared times the height. Okay? Now, from the equation that we just had, solving for that r squared is going to give us big R squared minus h squared all that time h. So, multiplying through, that's going to give us this cube. And now what we want to do is we want to find the critical point. So what we're going to do is we're going to take the derivative of that volume now, and we're going to set that equal to 0. So we're going to have this as a function of h. What that allows us to do is taking that derivative with respect to h will leave us with this equation right here. And then that must be equal to 0. So what we have to do now is we have to figure out when will this be equal to 0. So it's clearly when this piece right here will be equal to 0. So what's going to make this equal to 0? And in this case, what you're left with is r squared equals 3h squared. Gives you r equals root 3 times h, or h is equal to big R over root 3. Therefore, when b primed is less than 0 occurs when h is less than big R over 3 cubed, or sorry, square root of 3, or is greater than 0 when h is greater than big R over square root of 3. So coming from this, we therefore can tell that when R is equal to this, it's an absolute max. So what we're going to do now is we're going to go back to our volume h, knowing that h is equal to big R over square root of 3, and we're going to plug that in and see what it gives us. So we're going to have r squared times r over cube 3 minus r cubed over square root of 3 cubed. Alright, what that's going to leave us with is this right here. And further simplifying this equation, which is just simple algebra you can do on your own, will bring us to this answer right here. And that there is the maximum capacity of the cup